Next page, and hopefully, yeah, there it is. You look at the general rule, you're looking at NPR over R factorial, so that's just the operation we did. We took the permutations divided by the number of ways each individual pair could be rearranged, or the expanded rule, which amounts to the same thing. All right. So number 4 is really just doing the same thing, but with 3-person groups. All right. So in that case, I mean, it's really, I mean, we don't want to have to draw a diagram out for this, but we would have 5C3. All right. You pop that in your calculator, what do you get? $10. Is that surprising? Shocking, right? Yeah. Do you know why it's surprising, other than because I asked you whether it was surprising?
Well, I don't know, because the other one seemed like it was multiplication of the 2, and 5 times 3 is not 10.
Yeah. Yeah. So the last one we got a 10, but we had a 5 and a 2.
5 times 2 is 10.
Yeah, it seemed to fit. Now we got 5 times 3. Oh, well, that's not 10, so that doesn't work. All right, so it doesn't have that natural relationship, but it actually works out kind of nicely, because if you go back to the well, I'll just go back myself. It'll mess up the video, but the reality is, like, these rules are things that you can identify or invent on the fly. All right, so we have a couple of examples here, some a little bit, more challenging than others. Find the probability that of 5 selected people, no 2 share the same birthday. Now, the thing about counting is that we're not always looking for just the rule that you could apply, right? Sometimes it's a concept, an underlying concept that you're looking to get involved in the situation, right? So in this case, we're going to use the general theme of the topic, which is factorials, permutations, combinations, the idea of counting in general, all right, multiplying, all right, so consecutive values, things like that, right? So the spirit of these processes should come into play, but that doesn't mean you have to find like a 5C2, like a simple rule that's going to apply. Different people can come up with different courses of action and still come up with the same correct answer. What I like to do is kind of diagram out the situation. I got 5 people, and they're not going to share the same birthday. All right, so I got person 1, 2, 3, 4, 5. And what's actually going to happen using this approach? We're going to get at the idea of a permutation, but by the time we get at that idea, it'll be like, well, I don't need to write it as a permutation because I've written out all the numbers already. So you kind of write the numbers out to discover what the permutation is. And then from there, you're like, well, I don't need the permutation now because I already did the work, right? So no 2 share the same birthday, which would mean that all the birthdays are different. All right, so the first person could be born any day out of the year. So there's no restriction. Now we don't play around with leap years unless the question tells us to do that. So we just assume 365 days out of the year. So the first person could be born on any of the 365 days out of the year. No restriction. So it's kind of like we're figuring out the probability that the first person has a birthday. All right. Any of 365 possibilities. Now the second person can be born any day of the year except for the same day that the first person was born. So what's the probability? Yeah, 364 out of 365. And it doesn't take really too long before you figure out what the shortcut is. All right.
Oh wait, never mind. I was doing this without replacement.
Oh, gotcha. So the third person can't be born the same day as either of the first two people. So any of 363 days out of 365. And then you see the trend, 362, 361. Now you could, I mean, it's only 5 fractions, so it's something you could easily type into your calculator. I don't want to type it in like this though. What I'd rather do is type in 365 P5 over 365 to the 5th. That's going to be easier, right? So I'll pop in my fraction, since I remember how to use a fraction on this thing. Get rid of that. There it is. 365. Oh, actually, this one's different. So, fraction, and then math, probability, NPR, 365, 5, and then 365 to the 5th. Right, so you just have to remember to type in your n before you select the NPR function. Mine's slightly different.
How do you get the fraction to come up on here again?
Alpha y equals. And the benefit of putting it in fraction form is if it is something that can be simplified, it will simplify it for you. This one, I mean, it can be simplified. It's just a hideously large fraction. So numerators and denominators, so the calculators just go into decimals. So we're looking at 0.973, approximately. Now, I would think that would make some sense. We only have 5 people in a room. The probability that all the birthdays are going to be different would probably be pretty high. September 1st. Anyone else September 1st? No? Okay.
That's my mom's birthday.
Oh yeah? All right. So if it were campus night, then I would have a win there. When's your birthday?
February 4th.
February 4th. Any February 4ths?
June 9th.
June 9th? Kristen?
August 28th.
August 28th, anyone? Matt?
That's my little brother, but
Oh, that's your little brother. Yeah, so you see we're getting it, but we would need more people. Yeah. What do you got, Matt? When's yours?
April 19th.
April 19th? Or
August 31st.
August 31st? Oh, so close, because I'm September 1st, so it's like right there.
August 15th.
August 15th? Anyone? Yeah, it didn't look like that.
May 20th.
May 20th?
Yeah, I don't think we're gonna get it.
Doesn't look like it.
Yeah, June 12th.
June 12th?
No.
December 28th.
December 28th, no.
Yeah.
Yeah, I mean, we didn't have to do this in order to prove it. I mean, it's pretty much common sense, but, yeah.
I couldn't do this on-
actually, we would have had one if Frankie was here.
What, would,
Same as Sam.
Yeah.
oh, really? Oh, so we would have had it. So there you go. So we have 9 people. The 10th person would have been it. All right. So what we could do is figure out very quickly, because I just have to do a little second ender, what it would be if there were 10 people. So 10 people all having different birthdays, the probability would jump down to 0.883. All right, so still pretty likely that the birthdays are not going to be the same, but less likely than it was for only 5 people. All right, now, quick question. How many people would I have to have in order to guarantee that there would definitely be two matching birthdays?
366.
366, yeah. Because that would imply that the first 365 was that rare case where all the birthdays were different. That 366 person, that person would have to match one of the other people. All right. Now, part B is kind of weird because we talked about a rule for at least one. At least one is 1 minus the probability of none. All right. This has at least in it, but it says at least 2. Now, you could kind of conceptualize it by saying, wait a minute. if no two share a birthday, that means all the birthdays are different. If at least two people share a birthday, that's the opposite case, right? That's allowing for any matching birthday. Maybe all the birthdays are the same. Maybe only two people match and everybody else are different, or some kind of mixture. All right, but bottom line is this is getting at the idea that what we're talking about is 1 minus 0.973, which is approximately 0.027. So about a 2.7% chance that at least two people would have the same birthday. Now you might look at it and say, well, wait a minute, 1 minus that. I mean, that's fine, but the rule says at least one. You're kind of stuck on that. Well, at least two in this context so they're talking about at least two people, right? But conceptually, because here we're talking about birthdays, right? The probabilities that we're talking about here is the probability of each individual having a birthday that fits the criteria. So at least two people is like the commonplace way of saying it, but what it's really asking us to determine is the probability of at least one match. All right, so matching birthdays, all right, at least one match. So it's getting at the root of the idea that it is still an at least one situation, but it's kind of loosely that. Then the other thing you can kind of consider is, well, they are opposites. So the complement rule accounts for opposites, right? You're either going to have them, if you make it a binomial situation, you're either going to have them all be different, or in some capacity they're not all going to be different, right? That doesn't mean they're going to all be the same, but they're not all going to be different. That's what this is talking about.
I guess would this also be 0 out of 365 times 1 out of 365 times 2 out of 365 times et cetera, because of the number of available days to match, or?
Right. That's assuming that we're going all the way out to the 365th person, though. Now, I kind of already answered number 7, because it's really just what I did with the 10 people, just with 45 people. So, second enter. Oh, that got really ugly. Let me do it this way. So, 45. So, not really doing this because I think you need me to do it for you. I'm doing it because I think we're interested. That's the 46. I got to change that. In what this probability is going to be. All right. So, the probability that all the birthdays would be different for 45 people would be about 0.059. Probability, bless you, at least two the same. Is going to be 1 minus that. So we're talking about 94.1%, so about 0.941. So we didn't actually have to get out to even close to 365 in order to get something that, I mean, it's not certain, but it's more and more likely, right? So you get into a larger class, you know, like if you're taking a freshman English class or something like that, where there's 25, 30 kids in it, and the probability is going to be much larger. But you could see that it actually spikes up pretty quickly in terms of the probability, and then it starts kind of leveling off close to 1.
Now, what should we do in the event where, so I put in the 365 and figure out 45 and I get overflow error? What should we do in that case?
So that's what I was going to get to next. what we're going to actually do is generalize this relationship, and instead of saying 45 successes and all that jazz, what we'll do is let pick a variable, we'll say n equal number of people. So the probability at least two are the same would be equal to, if we generalize this, it's really just 365 p whatever this is. So in this case, I'm calling it n. Maybe I'll call it r, just to keep it in line with the formula. All right, even though n typically represents the number of values in a set, I'll just do it that way this time. All right, so I'd be looking at 1 minus 365 PR over 365 to the R power. All right. So what I would need in order to figure out this probability for large values, because we can't actually determine what it would be for large values because of the overflow issue. What we would do is find the limit as R approaches something reasonably large. In this case, you can come up with something that you think is reasonably large. You could just say 1,000. You could say 366 if you want. Or you could say 45. It doesn't really matter. Or you could say infinity. All right, and so we'd have 365 PR over 365 to the power of R. All right. And so we kind of run into a little bit of an issue in terms of the algebra of this, because expanding out the bottom is not a problem. Expanding out the bottom is just writing 365 times itself as many times as it would make sense to. On the top, it's definitely a different situation, right? Because what's happening here is you're starting off with 365 and then expanding out from there, but never going all the way necessarily. Maybe you are, but and I'm putting infinity in here as a placeholder, but the physical constraints of this make it so that infinity is not a practical value. Because if this value goes beyond 365, then you're going to have the factorial is 365p 365. You're going to have negative numbers, which would make sense. All right, but I'm using infinity because analytically we just care about where this function would be going, not necessarily how it gets there. So this would be 365 times 364 times 363 and so on. On the bottom, it's going to be 365 times 365 times 365 and so on. All right. So what I can do is at least simplify this component of it. All right. One of the properties of limits tells us that I can find the limit of each factor separately and then multiply them together later on. All right. So if I do it this way, I could say, well, the first piece is going to go to 1. I would have limit of 1 times the limit as R approaches infinity of everything else. All right, so 364 times 363 times and so on. All right. Now, the issue with that is it seems that we're kind of creating a circular logic issue. Because then I would say, okay, well, couldn't I just do that with everything else? You know, now I could split off the 364 over 365, and then the 363 over 365. So really, it's just a matter of determining where this is going. So you could use the calculator approach and simplify it a great deal, because again, it's not a calculus class, but there are some elements of calculus that are going to work its way in. All right, so let me just type in you can type in the original function, the simplified function. As we go out to infinity, this probability should be approaching a particular value. So the theory is that it would be approaching 1. So we have that. So if that's the case, this should also be approaching 1. So I would want to see how that plays out. But what I can do is I could type in as a fraction 365px. All right, so math probability, I'll put in my 365. I'll put in the variable x on the bottom, and then 365 to the x power. All right, so I don't need my derivative function. So I can create the graph, or I can look at the table. If I create the graph, there's some zooming that has to come into play. And that could be a mess. You know, I'm zooming all over the place and I'm not seeing anything. So no bueno there. But I can go into the table and see what the distribution is shaping up like. All right, so as I'm increasing, it does appear that my y1 is going to 0. All right, so it started off at a 1, but then it seems to be going to 0 as I increase the number of trials. So from that, I can infer, because it's 1 minus this, I'd be looking at 1 minus each of these, that this limit here, this piece, must have been a 0. And so I'm looking at 1 minus 1 times 0, which gives me the 1. So we essentially just proved that this is a probability distribution, but you know, in a more calculus-y oriented sort of way, right? And so one of the things that we're going to have to do as we move forward is not only come up with answers to probability questions. What we want to do is come up with functions that represent the probability situation. So they're known as probability models or function models. They're also known as probability distributions, because anytime you're talking about a graph or a table related to the outcomes for a probability situation, you're dealing with a distribution, a probability distribution, right? The idea here is that we can create a continuous function, right? So once we have that continuous function, we can do things like find the area under the curve for that function, which would give us probabilities over an interval, right? So what I could be looking at is, what are my, what's the sweet spot in this situation? Like if I wanted to have probability, the probability that matching birthdays would be, let's say, in the neighborhood of 80%. Like what number of trials would I have to have in order to be in that neighborhood, right? That's where this approach becomes more useful, all right? But this really is just determining what the probability is heading for as we go after a particular value. So I can look at, what was it, 45? Yeah, 45, so I can scroll down to that in my table because I created the function. 45, I got 0.059, which is what I got over here, all right? So if I want at least 2, I just subtract it from 1 and I have it, all right? So it's not bad, you know, just come up with a function, and then you can answer a bunch of different probability questions all along the way, all right? But that's why, you know, this is the like these kind of questions up here, these are like prob and stat. This is what makes it AP, all right? The fact that we're connecting to different sides.